let's start with convolutional neural networks. So in this lecture, we'll see like what are the different basic like building blocks of convolutional neural network, and like what's the fundamental operation which is being performed inside these networks. And then we'll also have like a case study. So in the agenda we have, first we will talk about like the overview to give you like some high level idea where these CNNs are used. And then we'll try to go through some of the basics which we have already covered like in the past lectures, but which is relevant to this topic. And then we will directly jump into the fundamental operation, which is the convolution operation, or you can say correlation operation. And then some practical considerations, like some things which you should be aware of when you're designing a neural network. And finally, a case study where we'll take like a well-known CNN architecture and try to understand like how it works and what are the different components there. So let's start with the first segment, which is the overview of CNNs. And before that, like some very interesting example to you. This is just a joke, so not part of the lecture. So these days, like when you're working on deep learning, usually like it's very fascinating, right? A lot of people, I mean, they're very interested, and most of the fields are actually interested in this area, and they're trying to use deep learning into their research. Okay, and for the general society, it's like a very big deal, like the kind of impressive results we have. And so this is just like interpretation, what different segments of the society thinks about like when you're working on deep learning. And this is also interesting because the deep learning job market, it's so hot. When you will see like when you graduate, like it will give you like very high paying jobs, and the job market is really good at this time. And other scientists, I mean, they might not be like getting that much of like in terms of salary. And this is also interesting because mathematicians, like everything they do, it's like well grounded in theory. But you will see like in deep learning, when you design your networks, when you train your networks, of course, we have like some kind of mathematical background, but most of the time there are a lot of heuristics involved. So a lot of hit and trial. So that's one of the like limitation of deep learning at this point. And a lot of researchers are actually working on grounding like whatever findings we have, the interesting findings, to some kind of theoretical background. And if you think of yourself, you know, and this is a very famous scientist, Jan LeCunte. So you think you're doing something great, but actually most of the time, you will see in the programming assignment as well, you're just using existing code, right? You will see like if you use PyTorch, you're just importing like different library functions. And even for training, you don't have to write a lot of code. So basically it's not like a lot of effort, but this is a different perception, like different segment from the society has. Now, another motivation for you, I think some of you might have seen like this in the news articles. In one of the like art contest, someone actually created this image using AI. And this was, I think, some version of DALI model. And this actually won the prize. And the artists were really not happy about this because, I mean, even though this looks really nice, but I mean, no one created this, right? It's just like AI generated. So something to think to think about, but this is exciting. And these days you will see like a lot of people are actually trying to do that. They are creating these arts and they are selling them online, and they are sometimes getting paid a lot. Okay, so that's one aspect. But if you look at like the results, I will show you like one simple example. And the problem here is, given a video, just a monocular video, can you estimate the depth of each pixel? And the problem says like, in this video, like whatever pixel you choose, can you tell like how far that pixel is from the camera or the camera viewpoint? And I will show you example like a CNN-based model can actually do a pretty good job. So the animation on the right, it shows like the depth of each pixel, and you can see like if you compare that with the input video, it's actually doing a very good job. And with like so there are a lot of applications of this depth estimation. One interesting application you can see is like you can actually create a stereo effect, because if you have these sequence of frames and you know like depth of each pixel, then at like certain time step you can actually kind of extrapolate or predict like what are the hidden pixels, because you know the depth, right? So this is again just one example or one application of depth estimation. There are a lot of others as well. So I think this is a pretty cool example to show like how powerful these CNNs are. Some more motivation. This is like the problem is super resolution, and the idea here is given an image which is like very bad resolution, which I'm showing you on the left. But you can see it's a very pixelated image, and you can use CNNs to actually convert it to a very high resolution image. So the input is on the left, and on the right it's like as the model is being trained, how the noise is actually being converted to the high resolution image. And you can see like the final result, it's really amazing, the quality of it. Okay. Now let's try to understand and get an overview of these CNNs. So these again are a class of neural networks. The difference is they will take images as input. And I'm saying mostly because they might not take images, they might take something else as well. Okay. And what they will do is, given that image as input, they will make predictions about that image. And depending upon like what problem you're trying to solve, they will the prediction will change. If it's classification, they will say that, okay, if the class is present or not. It could be localization, then they will have to give the bounding box as well, and so on and so forth. A basic structure of a convolutional neural network will look something like this. And again, it will vary a lot, but most of these components will be there when you train or when you build your own convolutional neural network. Okay, so let's try to understand the components of this architecture here. This is the input. So this is the input image, and it could be grayscale image, it could be a colored RGB image. Depending upon that, it will have like, let's say 1 or 3 channels. And then another important parameter is the resolution. Okay, that will like what's the height and width of this image. That will define like how many pixels you have. Then the second layer, usually you can say the first layer is the convolution operation. Okay, the layer is not being shown here, but these arrows actually represent that layer. So this will be the convolution layer, and this layer will actually convert this image into some form of feature maps. Okay, if you remember, like in the previous lecture, I said you are going from volume to volume. So in this case, the input volume is this image, and the convolution layer is actually converting that to another volume, which are the set of feature maps. And don't worry about like what these feature maps are, how we get these feature maps. We are going to go into detail of that, like every bit of that. So at the end of this lecture, you will be able to understand like what we are trying to cover in this overview. Okay, so then you might have some kind of subsampling where you try to reduce like the number of activations or feature maps you have. And you will see I will use the words feature maps and activations interchangeably. So both means the same thing. Okay, it's actually corresponding to the data which is flowing in your network. So then if you do subsampling, then the size of these activations or the feature maps might reduce. And then again, you can have more convolution layers. Again, you will get like set of feature maps. Again, you can have subsampling, you can reduce it. Then eventually you will have a fully connected layer, which will give you the prediction. And this fully connected layer is actually the MLP, the multi-layer perceptron we were discussing earlier. Okay, so that is also a part of your CNN architecture. And again, it depends. Like some of the recent CNN architectures, you will see that you don't have this fully connected layer. But again, that's just a variation. So it's an option whether you want to use it or not. But the earlier CNNs, they used to have this fully connected layer to give the final prediction. Now, the CNNs are not like recently developed. And I think in late 90s, I think in 1998, the photo I showed you earlier, Jan Lukun. So they developed this LANET architecture. And if you look at this architecture, it actually resembles the one I showed you earlier, right? Exactly the same thing. The only difference is we have a grayscale image. And again, that's due to like the computation power. Back then, we didn't have like the powerful GPUs, right? And you can see like the input resolution, it's just 32 cross 32. But rest, it's the same. I mean, you have the convolution layer, you get the feature maps. This is subsampling, you reduce the feature map, convolutions, again, some transformations. Okay. So whenever you are applying these convolutions, you're actually transforming your activations to a different set of activations, or you're transforming your input image to like some set of feature maps. So that transformation is going on. And that the transformation is nothing but like the linear combination, or you can say the filtering operation, which we have been learning like throughout this course. And we'll come to that. Okay, then we have this fully connected layers, and in this case, we have two fully connected layers, and finally like 10 outputs. You can see this resembles like the multi-layer perceptron, which we discussed in the previous lecture. So 10 outputs because I think it was developed for digits. So if it's digits, then 10 outputs. Of course, for characters, like you might change it to 26. Okay, so CNNs are not new. People have been working on this prior to this. The issue was back then we didn't have computation power. We didn't have enough data. So the first strong results, they came in 2012. And the architecture was called AlexNet, and we are going to do a case study on this architecture later in this lecture. So the reason was not like innovation in terms of architecture. AlexNet, in fact, used the same architecture which we are seeing here in Linux. Okay, so the only difference was the availability of data and the availability of computation, like a lot of computation power. Okay, so what happened in 2012 was there was a ImageNet or image classification competition, which used to be there like in computer vision community. It's still there. So this was called like a large scale visual recognition challenge, and researchers were like improving every year, maybe 1 point or 2 points. But in 2012, the error rate was improved by like almost more than 10%. So it dropped from 26 to 15. So the next best entry was 26%, which was not using CNNs. So this was like a big breakthrough. And that's when like the deep learning revolution started. And that was the architecture used in AlexNet. And you can see like it's almost same as what we saw in Linux. Okay, this is the input. And again, we are going to talk more this architecture in more detail when we do the case study. All right, so it started in 2012, but today, I mean, CNNs, they are used like everywhere in all the problems, right? And this we have covered in the first lecture as well. We saw that we use CNNs for classification, we use them for object detection, we use for semantic segmentation. And later in the course, we will talk about some of these architectures of these CNN architectures, which are very popular and very, very good in, let's say, object detection or object classification. I mean, they can be used for image captioning. We have talked about style transfer as well. Now, earlier I said like images are used as input mostly. So what I meant is we can use like some other kind of modality as well. Okay, so we can use natural language as well as input to CNNs. And the idea here is, let's say we are doing text classification. So what we do is, if this is your sentence in some of the languages, okay, so a sentence will have a sequence of words. What we do is each word can be converted to a vector. And there are different ways to do that. We will not go into detail of that. So word to vector is one such algorithm which converts each word into a vector, let's say of 300 dimension. Of course, you can have like 100 dimension as well. So what you can do is you can convert each word into a vector. And for a sentence, if you stack them together, that's going to give you a matrix. And then you can, if this is a matrix, you can use CNNs. All right. You can use this for audio research as well. Audio is like just one-dimensional signal, but you can represent that one-dimensional signal as a spectrogram as well, which looks something like this. And once you have this like a matrix form of input, you can apply CNNs. So if you can convert your data to a matrix format, either 2D matrix or 3D matrix or 4D matrix, then you can use CNNs. Okay, so if it's audio, you can use 1D. And this audio is like, you can even like just take the raw signal. You don't have to even convert that to spectrograms. All right. So it will change the operation you are using. If it's a one-dimensional signal, you will use 1D convolution. If it's high-dimensional, let's say videos, you will use 3D convolution. All right. For images, it's 2-dimension. So you use 2D convolution. So we'll see like what are the basics which will be required to understand like these convolutional neural networks, and all these basics we have already covered. So I'll just give you a quick recap of this. Okay, so the general CNN architecture we have already seen. We have this input as image. We have convolution layers, subsampling layers, again followed by convolution. And again, we can have several of these layers. This is just one combination. And at the end, we have like fully connected layer, which will give you the predictions. Of course, you can have more than one fully connected layer. Okay, so that's the input. Now let's talk about the input. So input can be, again, it could be one-dimensional signal, 2D, 3D signal. So let's talk about images. Images, we know it's like you can store that as a two-dimensional matrix, and it will have like certain height, certain width, and for each pixel location, or you can say like this grid location, you will have some value. For grayscale, it will be just one value. If it's RGB, you will have three value. Okay, so usually we work on RGB images. In that case, you will have a volume which represents the image, and that volume will be like three-dimensional volume representing height, width, and the depth. So depth in color, in case of color images, will be 3. In case of grayscale images, the depth will be 1. Okay, so that will be your input to your CNN. The second part is the network itself. And this part is like the convolutional part of this architecture, which tries to learn, or you can say extract features from this input sample. Okay, so that's the whole role of this part of the architecture. And once you have these features, you can use those features to perform the classification task. All right, so let's try to understand how this part of segment is actually extracting features. For that, let's go back to filtering. Filtering, we have seen, given a filter and your image patch, you perform this linear combination, right? So if this is your image, this is your filter, it gives you some kind of response. And the idea was it's trying to do some kind of pattern matching. So whatever pattern you have in your kernel, if that pattern is present in your input image, you will get high activation. Otherwise, you will get a very low activation. Okay, so if this is your image patch, again, it's a very small patch of a big image, and this is your kernel, all you do is you perform filtering, which is just element-wise multiplication of these values, and you can just take the mean, you can just add up those values. Okay, so this is the basic filtering operation which is performed inside your convolutional neural networks. Okay. So this filtering, I mean, you can have two variations. Either you can find correlation, or you can perform a convolution. We'll briefly talk about that, what's the difference. And the basic difference, like conceptually, we know that they are basically the same set of operations. The only difference is you have to like flip your kernels in both the axes to match convolution with correlation. Okay, so this is the basic correlation operation. It's just taking element-wise multiplication and adding up the values. And convolution is if you flip your kernel, then you can again perform the correlation operation. Okay, so you have two extra steps. And we talked about edge detection, where what we did is we have this Sobel kernel, which was, and you are also doing this for a programming assignment. And it's trying to, if you look at this filter, it's actually trying to find edges. That's what this filter represents, because the values are changing in the X direction. And in this one, the values are changing in the Y direction. Okay, so that was the algorithm for Sobel. But the idea is, again, you are just doing filtering here. And what you're doing is whatever filter you have, you're trying to find that pattern in your input image. If this pattern is present, your outer activations are going to be high. So that's the whole idea about this center segment of your convolutional architecture. You will have these kernels here. We'll talk about that later. So those kernels will try to find the patterns in the input image. Okay, and it's not just one step. You will keep finding that patterns as hierarchy. So you'll find patterns in the input image, and then you'll try to find patterns in those patterns, and you keep doing that. So that's kind of a composition. And at the end, that's going to give you features, which you are going to make. I mean, classification, you can use those features for anything. For classification, for detection, or semantic segmentation. Okay, so this final layer, as I said earlier, it's like a simple, fully connected layer, which is a multi-layer perceptron, and we just discussed this in the previous lecture. So the extracted features from the image are treated as input to this MLP, and then we make predictions about like what, let's say, image classification, what object is present in these set of features. Okay, these are also called feed-forward neural networks. Now, so that was like a brief overview, and we have also seen this learning process, the whole pipeline, how we train these models. So again, we don't train on like single images. We have like the full training set, right? Given a huge data set, we split that into training and testing and validation. So these features in case of CNN are extracted by that CNN part. All right. So this CNN part will give you these set of features. So this, I think we just covered in the previous lecture, like what's the difference between neural network and convolutional neural network. And one big difference was neural network actually worked on flattened set of features. We don't preserve the spatial structure. In CNN, we are preserving the spatial structure. So that's one positive. The other is like, while we are doing that, we are able to actually share the weights. So which reduces the memory consumption of the network. And later we will, when we do the case study, we'll see that like how that reduces the amount of weights we need in a network drastically. Now, the next segment is we'll try to understand what is the fundamental operation which is performed inside these convolutional neural networks. Okay, and that is the convolution operation. So that's kind of funny. Later you will see that it's actually not convolution. All the libraries which you will see, they actually just use correlation operation. So if you can, if you want to call these like correlation neural networks, perfectly fine. It's just a term. But you also know, I mean, mathematically, it's not like a big deal, right? Both are almost same operations. And later you will see like why it doesn't matter whether you perform convolution and correlation. We'll briefly talk about that. Okay, so this is the core building block, the convolution operation, and also you can say the correlation operation. Okay, so what happens is we try to preserve the spatial structure of image. And if let's say this is your input image of resolution 32 cross 32. So this means that 32 pixels in height, 32 pixels in width, and 3 pixels in the channel dimension, right? So this is your input image. You have these filters. In this case, the shape is 3 cross 3 cross 3. All right. So these filters are weights of your convolutional neural network. So in case of neural networks, the weights were those arrows, right, which are connecting the input to the neurons to perform the linear combination. In case of CNN, these filters are the weights. And by weights, if you try to understand this, we don't estimate these values, we learn these values. Okay, so these filters will be learned from data. And that's like that's a very important point here. I mean, that's why these CNNs are very, very powerful. Because if we have to handcraft these filters, I mean, again, it will have some kind of biases, right? It won't be that powerful if we try to learn these on the data. So if we are training these filters on huge amount of data, so this learning is like automatic, which makes this very, very interesting. Okay, otherwise, this is same as like the classical algorithms, where, for example, Sobel algorithm, right? We have that kernel, which was not learned. We just use our knowledge, but still it was doing a good job. But in this case, we are learning these filters. So that's a big difference. So this filter is the weight of your CNN. And what you do is you convolve this filter on your input volume. Okay. So right now, what I'm showing you is this is an input image, but treat this as like it could be anywhere in your network. This could be this could be like your input image, or this could be like feature inside your network. Because as I said earlier, your CNN is actually transforming volumes to volumes. So you will go from volume 1 to volume 3 to volume 4. You keep transforming them. So this volume could be at any stage in your network. The operation is not going to change. It will be the same set of operation. All right. So in this case, it's input image, which is fine. So we have this filter. We will convolve this filter on this feature volume. So I will call this activation map or feature volume or feature map. All these mean the same thing. And you know how to convolve, right? So this is 3 cross 3 cross 3 filter. You will try to put this at like all the possible locations in this feature map or this input. And if you place, let's say at this location, so at this location, you will have again 3 cross 3 cross 3 volume from this blue cuboid. And you have like 3 cross 3 across 3 values from this kernel. You will just perform the element-wise multiplication. You will add those values, and that's going to give you just one number. So that's just a very standard correlation or convolution operation, which we have seen like a lot in this course. All right. Instead of like 2D, it's a 3D. That's the only difference. So another point, you will see like this is called a 2D convolution, right? But the kernels you are using, it's 3-dimensional kernel. The kernel is not 2D. Okay, so that's one thing to note. And if you are performing 3-dimensional convolution, your filter shape will be 4-dimensional. Okay, so now what happens is you take this filter and applying at one location gives you one value, but you just don't stop there. What you will do, you will apply at all the possible locations. All right, so you have seen like the sliding window approach. We have talked about that earlier. And that's going to give you an activation map or a feature map, which will have like similar spatial structure as your input feature volume. So don't worry about the dimensions of this. So input was 32 cross 32, and this reduced to 30 cross 30. So we will talk about that, how the dimension will change. But at the end, you will get a lot of these values, right? Because you're applying at all the possible locations. So you create feature map using this. So this actually covers 2 points. One is we were talking about weight sharing. So you can see that we are just using the same set of weights or the same filter at all the locations to get this activation map. So that's how we are sharing weights. The second question was, I think someone was asking about programming assignment 1, that whether we want to preserve the shape of the input image when we compute the gradient. And of course, gradient is also filtering, right? So it's actually the same operation. So in this case, we are not preserving the weight. So we are going from 32 to 30. Okay, so this is like a single convolution operation inside your convolutional neural network, which is happening. And what you do is you don't just use one filter, you use multiple filters, and not just 2 and 3, a lot of these filters. So what will happen, for each filter, you will get similar activation map. Okay. So these set of filters represents one convolution layer. So when you're saying that, okay, you have a convolution layer in your convolutional neural network, so that convolution layer is nothing but these set of filters. And the operation that layer will perform is, it will take each filter, perform this filtering operation on all the possible locations, obtain this activation map, and repeat the same process for all the filters. So if you look at this, you are actually going from volumes to volumes. It's just like the shape is changing, which is fine. We'll talk about that, like how to preserve that or if you want to change it. But the bottom line is we're going from volume to volume and we are sharing weights. Okay, so your convolution layer, as I said, it's just like set of kernels. Now let's try to understand that using a very concrete example. Let's say we have a convolution layer where we have 6 different kernels, and each kernel has shape 3 cross 3 cross 3. This was your input image, height and width 32 cross 32. It has 3 channels. It's a colored RGB image. And this convolution layer, which has 6 kernels of this shape, will give you 6 different activation maps, right? Because 6 kernels, one kernel is going to give you one activation map, 6 will give you 6. And that's why the depth of this activation map is 6. And don't worry about 30 and 30. We'll talk about how we got from 30 to 30, but do try to understand how we got this 6. So this 6, the 6 is a result of like how many kernels we have. So if we would use like 60 kernels, the depth of this activation map will be 60. Okay, so that's one important thing. The second important thing which you should understand on this slide is the shape of this kernel. Okay, so as I said, we are performing 2-dimensional convolution, but the kernel shape is 3-dimensional. So the reason is the third dimension of this kernel, we have no control on that. Okay, we can only control the first 2 dimensions. So usually you will see that in your CNN, when you're developing 2-dimensional convolution neural network, you will only say that the kernel is 3 cross 3 or 5 cross 5, 1 cross 1, 7 cross 7, because the third dimension is implicit. And the reason is the third dimension is actually determined based on the depth of your input feature map. In this case, image is the input and you have 3 channels. And therefore, the third dimension of this kernel is, it has to be 3. So it doesn't matter how many kernels you use. For all the kernels, the depth will be 3. All right. And you can also only design the first half. So in this case, the kernel is 3 cross 3. Okay, so that's one important part. Second is like how you get the 6. So with that, I mean, if you have another convolution layer after this activation map, so one thing is predetermined. Irrespective of what is the size of a kernel, the third dimension of that kernel will always be 6. All right. So then what you can do is, this is one like convolutional neural network with one layer. You can just stack like these convolution layers on top of each other. Okay, so that's the first layer. Then you can add one more layer. In this case, the second layer is, you have 16 different kernels. The kernel size is 5 cross 5. And you can see the third dimension we can't control. So 6 is coming from the depth of the input feature map. Because that was 6, that's why we have 6. And again, so this 16 will give you 16 different activation maps, and that's why you have this volume. Of course, the X and Y is actually going from 28 to 24, which is fine. As I said, we'll talk about that later. So that's how, so this is like a 2-layered convolutional neural network. You can just keep building layers on top of these. Okay, the layers, the operation will not change. So again, so what I'm going to do is, we started introduction to convolutional neural network, and we already went through the fundamental operation, how the convolution layers are formed. So I mean, I will quickly go over like those slides today as well, just to keep you in touch as we proceed in this lecture. Okay. So what we're going to do is, we are going to first go through this fundamental operation and then talk about like other aspects of convolutional neural networks. So as we discussed, the core building block of a convolutional neural network is a convolution operation or a correlation operation. And the idea is, we try to preserve the spatial structure of your input. And as we process your data in this network, we go from volume to volume. And to be able to move from volume to volume, we have to perform this transformation using the filtering operation, for which we use these filters. Okay, so this is just doing one filter, which is actually applied at all the possible locations of this input. And for each location, we are going to get like one response. So we collect response from all the locations to get an activation map. And of course, we have like multiple such kernels. And that's how we go from volume to volume. Okay, so and these kernels actually these kernels actually form a layer inside your convolutional neural network. Right, so once you have this convolution layer, which is nothing but like a set of kernels, and the only parameters are how many kernels you are going to use and what is the shape of these kernels. And then again, using these kernels, you apply a filtering operation on the input and you get the output activation map. And this constitutes like a one layer of your CNN. You can actually stack multiple such layers on top of each other. And again, you are going from volume to volume. So you start from the image, which is again considered as a volume. And depending upon like how many filters you have, what is the shape of those filters, you will have certain shape of these activation maps. And we talked about like how the third dimension of these filters should match the depth of the input volume here. In this case, it's input image, which has 3 channels for R, G, and B. So therefore, we have to match this depth with the third dimension of the kernel. So we don't define that. We only define the first 2 axes for these filters. So that's one point. The second point was the thickness of these activation maps is determined by how many filters you are using in this particular layer. Okay, so for example, in this case, if we are using 6 different filters, the depth is going to be 6, because for each filter, we are going to like get a flattened feature map. Okay, so those are the 2 important point which should be noted here. And the dimensions, like why we move from 30 to 28, what is the role of like what kind of filters we are using, we are going to cover that later. And then you can see like So one interesting thing I think which we didn't cover last time was, so it's fine, I mean the depth should actually match. So when you're matching the depth, what's happening is when you're placing this kernel at any location, then in the spatial region, you are actually covering 5 cross 5, which means like the 25 pixels which are in the neighborhood, right? But in the depth aspect, you are actually covering all the pixel values, okay, at once. So you're spanning across spatial dimension like X and Y, but you're not spanning across depth. So you're considering all those values just just like a single time, right? So all the values are considered when you compute the linear combination of all the activation maps. Okay, so that's one thing to note here. Let's talk about when we say, okay, a convolutional neural network has like certain number of parameters, what exactly that means. And this we have already seen in neural networks, where we saw that like the arrows which are actually going from input to output neuron. So those weights are the parameters, and those parameters are learned. So let's try to understand what are parameters in these convolutional neural networks. Let's say we have a certain volume. You can say like it could be input image, or it could be a feature map in between your CNN. Okay, so the shape is 32 cross 32, depth is 3. And let's say we are using a filter of shape 3 cross 3 cross 3. As we discussed, if you apply this at one location, it's going to give you one number. And then you convolve over all these spatial possible locations, it's going to give you activation feature map. All right. Now, this blue block over here, these are activation values. Like it's kind of a response of your network on whatever features were coming in from the previous layer. All right. And if it's an input layer, if it's an image, then these are just pixel values. Okay, so these are data points, which means these values will change with like different samples. And these are not parameters. Okay, so these values are not defined by the network. It is property of the data. Again, these activation maps, these are not parameters. This is kind of a data flowing in your network. So these values will depend upon what kind of features were present in the previous layer. All right. So these are not learned. These are just like showing how your data is flowing. So then what exactly are parameters which we are trying to learn? So these filters over here. Okay. So let's say if we just consider one filter, which is 3 cross 3 cross 3, which means this filter will have 27 different values. All right. So those 27 different values are actually used when you transform this input volume to the output volume. All right. So those values are actually parameters. They are independent of what input sample you will use. Okay. Let's say you select like image number 1. This filter is not going to change. It will remain the same. The only values which will change is this blue block over here and this orange block over here. And if you pick another image, again, the values of blue block will change. The values of orange block will change. The values of this filter will not change. Okay. So then this filter is actually the parameter of your network. And this filter is defining how this activation map is actually transformed from like this stage to a different stage. Okay. So which means if we just consider one filter, we have 27 different parameters. And we were talking about like sharing of these parameters. And we are sharing because we are applying the same filter at all the possible locations. Okay, so that's what like parameter means in a convolutional neural network. So let's say you have this input image and you have a convolution layer, which is like some set of filters. And let's say we are using 6 different kernels or 6 different filters. So I will use like these terms interchangeably, kernels and filters. We have seen it means the same thing. So we are using 6 different kernels, and the shape of the kernel is 3 cross 3 cross 3. So that constitutes like this convolution layer. And if we use this convolution layer on this input data, we'll get something like this form of activation map. Now, if we have to say, okay, how many parameters we have in this particular convolution layer, we can just count these parameters. Okay, so this is going to give you 162, which means this convolution layer has 162 different parameters. Similarly, you can actually create, you can have more than 6 kernels. You can have as many as you want. And that will change the number of parameters you have. So one thing which will change the number of parameters is how many kernels you're using. The second thing which is going to change the number of parameter is what is the shape of your kernel. Okay. And then you can stack like these convolution layers on top of each other. And if you compute number of parameters for one layer, you can just add like for all the layers. And then you can say that, okay, this whole network actually has these many number of parameters. So now let's try to understand the convolution operation. I will give you like some more insights. What exactly is happening when we are performing this operation? Of course, we have seen filtering, like how it works and what this filtering actually means. So let's say we have a function ft, and you can see it's a simple step function, or you can say like a unit function. And from negative infinity, it's at 0. And as you come to this point, it directly jumps to 1 and stays there, and then comes down and again remains 0 as we go to plus infinity. So that's a simple function. Let's say we have a kernel, which is like almost have like similar kind of structure. And again, this kernel is like, if you go negative infinity, it's 0, goes to 1, comes to 0, and it stays there. Okay, so in this case, this is the function, this is the kernel, and of course, these are like just one-dimensional functions and kernels. But whatever we are trying to discuss here, you can easily generalize that to 2-dimensional or 3-dimensional or any high-dimensional space. Now, if we convolve these two functions, treating this as kernel and this as function, now what exactly is happening? You know that when you convolve, you actually you flip your kernel, right? In this case, if you flip, it doesn't matter because it's kind of symmetric. It's just like your plus infinity will go to negative infinity, and negative infinity will go to plus infinity. Okay, so that's one thing. Then what you do is you try to apply this kernel at all the possible locations for this function f. And those locations will start from negative infinity. Of course, I'm not showing negative infinity here. We are starting from -2. Of course, you can extend this to negative infinity. And on the positive side as well, you can go to plus infinity. So you start from this point, you take your kernel, and then you find the correlation. All right. So what you see, this kernel is actually not matching with the function at this location. Okay, so the response will be 0, because you know that it's just element-wise multiplication. In this case, it's just 1D function, and we just have two values, either 1 or 0. And at this location, if you put the if you apply the kernel gt has value of 1, but ft, the function, has value of 0. If we take element-wise multiplication, that's going to give you 0. All right, so it's 0. Now what you will do is you will stride your kernel towards the right. Okay, and then you will keep computing that convolution value. So you keep moving towards right, and you can see like still it's 0, it's 0, it's 0. But as soon as you reach like this location, you're seeing like some kind of overlap between the kernel and the function. Because what's happening, if you look carefully, like this red region here, at this point, it's starting to overlap, and which is indicated by this yellow color here, right? So the area of this yellow color actually shows how much overlap you have between function f and kernel t at this particular time step. Okay, so then you will see as you keep going towards right, the overlap is actually increasing, and at the center over here, they will perfectly match with each other, and you see you will get like a highest response. Okay. So this black plot over here, this is actually showing you the result of convolving kernel G with function T. Okay, so you can see like from the left, it's 0, it's increasing. At this point, there's a perfect match. Then again, it goes down to 0. Okay, so that's the standard convolution operation between two functions in a continuous space, you can say. I mean, of course, this is not like continuous, but still it's better than discrete. Okay, because we're trying to like apply at each possible location. So if you think about this, what's happening, when you are trying to convolve a function in a kernel, of course, output is like some kind of response. And if the structure of the kernel matches with the structure of the function, you will get a very high response. Okay, so that's the key. We have like discussed this several times, and it will keep coming. And that's exactly what we're looking for. If you can match the pattern, you will get high response. If you don't match the pattern, you will get a low response. Okay, so that's the whole purpose of performing this convolution operation. And this is like the continuous equation, which we have seen earlier as well. Okay. So this is one-dimensional, but in convolutional neural networks, usually we use 2D kernels, or you can say like 2D convolutions. So you can just extend these 1D functions to two-dimensional functions. In that case, instead of like looking at patterns which are one-dimensional, you will look at two-dimensional patterns. But the intuition remains the same. You're just trying to do pattern matching. And one example, which I think when we're talking about edge detection, this is a very interesting case of a convolution, you can say. So here the kernel is kind of, you can say it's an edge, because we are going from positive values to like 0 and then towards negative. All right, so this is kind of an edge you are seeing here. And this pattern is actually something which we are trying to find in the input image. And this is something for the edges in the y direction. So even when we're trying to perform Sobel edge filtering using these filters, we were trying to find these patterns in the input image. And if we were able to find this pattern, we get a high response, and that's how we detected those edges. Okay, so in this case, if you think about the convolutional neural network, the structure I showed you, the input image is the, let's say, some kind of volume you have like in your network. In this case, it's like input volume. And these are the kernels. In this case, these are handcrafted. But for CNN, we are going to learn these kernels. Okay, so these are the kernels, and these are the output activation maps, which we are going to stack together to again form a feature volume. So in this case, if we have like two different kernels, we got two different activation maps. We can have several other kernels. We'll get like similar, like the activation maps corresponding to those kernels. And then we can stack together all these activation maps together to be again like fed to another convolution layer in your architecture. So let's try to understand this operation. I will show you like several visuals so that everything is clear and there is no doubt once we are done with this lecture. So let's say this is your input image patch. And in this case, it's a binary image. So 1 represents like a very, you can say like foreground, and 0 represents background. So in this case, you can see like this is some kind of, in this area, it's highly active. And this is kind of background, right? So in this case, if we try to use a filter like this, if you try to visualize what this filter represents, it's simply a cross, right? So then ideally what should happen is if you use this filter over this input patch, it will give you activation map, which will represent which location you are able to find these crosses in the input image patch. Okay, so if you carefully analyze this, I mean, we don't have any crosses at all. Right, we do have partial crosses. For example, you can look here. So this side we have, but if you look at the other axis, I mean, this is kind of half cross, right? If this would have been 1, this would have been a perfect match. Then let's see like what will happen if we try to convolve this filter on this input image patch. So you can apply like at this location, again, it's element-wise multiplication. You know how to perform filtering. You just perform element-wise multiplication and add those values. It's going to give you 4, 3, again a 4. You can keep doing that. Okay, so now if you try to analyze like what kind of activation map you got, the highest value was 4, right? And you got that value at 3 different locations. So if you try to analyze what the input image patch was at these locations, then it was kind of partially matching with the cross. Not a perfect match, but still it was like some kind of match. Okay, even at this location. And the lowest value is 1, which is at this location. And you can see that it's the only match we have is for this location, right? If we try to create a cross here. And that's why it was like very, it was not highly active. Okay, so let's try to look at it with a more intuitive example. For example, if this is your some kind of activation map, if you try to visualize this, we have like activity in this region, right? And this shape looks something like this. Okay. Now, if this is your input image, the triangle shape, and let's say we are interested in this location. Okay, so it will look something like this, and this is the input image. And if our kernel is something like this, which I showed you earlier, you can see like this actually is matching perfectly with this kind of shape, which means that if we are using this filter to convolve this image, then if you try at this location, you should get like very highly activated values. Okay, so the response should be very, very high. Because on the left, it's like patch from the image. And on the right, that's our kernel. Of course, like they look almost similar. That's kind of deliberative. So if you convolve these two, you can see that it's just element-wise multiplication. For all zeros, you will get zeros. And for all ones, it's a perfect match. So you will get 1. And you can just add those values. It will give you 5, which is like a big positive number, which means that the kernel was actually matching with the input image patch. And in a way, which says that, okay, we found this match. Now let's try to apply the same kernel at a different location. And it's the same image, but it's just a different location. Okay, so the input image patch will look something like this. And you can, if you try to just binarize this, you will have these values. You can select that L kind of shape can be represented using these values. Now, if you convolve this with the kernel we had, which was this shape, then you can perform the convolution operation and you can see that it's just going to give you number 1, which is much smaller than 5, which means that you were not able to find the pattern you were looking for in the image. Okay, so then the idea is, of course, using one filter, we can find that pattern. But the interesting aspect is we don't just use like 1 or 2 filters like we were doing in the case of edge detection. We try multiple filters, and each filter is trying to find a pattern which is actually the pattern it's carrying itself. All right. So if we have like a set of these filters, then we can actually find all those patterns in the input image, and then depending upon that that pattern matching, we can say that, okay, if some set of patterns are present, we can actually use that information for inference for any kind of downstream task, whether it's classification or something. So that's in a way is trying to find features in your input images. Okay, so if you think about this, let's say you have these two different filters. So when you're trying to apply this filter in your input image, that's, let's say, if it's going to give you the green activation map, if you try to interpret this, and so this green activation map is actually just telling you at which locations in this input image this pattern was present. Similarly, the orange map here, it's just telling you on which locations in this input image the pattern of the second filter was present. Okay. So let's try to see that using the simple example. And again, this is something we have seen in edge detection. You will have your input image, and you will have different set of kernels. In this case, I'm showing you 2 different kernels. The first kernel is, let's see, the red one, which is like a edge slanting towards left. So if we used that filter to convert to the input image, you can see like you will get the feature map something like this, which is trying to find all the edges which are in this direction. Similarly, the green kernel, you can see that's an edge in the right direction. That's another kernel. Again, that will give you a feature map, which will be highly active in those locations where you have edges which are slantly like leaning towards right. And again, these are just 2 kernels. If you have lot of such kernels, you can find like very interesting patterns in your input image. It can be used for feature extraction. So the next part of this lecture is we'll talk about like different practical considerations like regarding the shape of those volumes. So when we are moving from volume to volume inside a neural network, how that shape is actually controlled and what we can do about if we want like any specific shape. Okay, so let's try to go over like again this convolution operation. For example, if we have a 7x7 map, and again, this is like some patch from your image, or this could be your input image, or it could be like any activation map, like intermediate activation map inside your neural network. In this case, it's 7x7, it could be anything. And let's say we have a filter 3x3. Now, what will happen is when we are trying to convolve, the idea is to place this filter at all the possible locations in this feature map. And as you can see, like this is the first possible location if you start from like left and top. So you are placing at this location. You can't place at this location because we don't have any values in the neighborhood. Okay, so that will be the first location. So you will get one value for this location. This could be the second one, and you can keep going towards the right. So you can see that as you stride like from left to right, you are able to place at 5 different locations, starting from this one, 1, 2, 3, 4, and 5. So if you're able to place at 5 locations, which means you are going to get 5 different activation values as you move from left to right. And the same thing will happen if you move from top to bottom. So that will result in an output activation map, which will have resolution 5x5. Okay, so which means that if you have an activation map of 7x7 using a 3x3 filter, your resolution will reduce from 7x7 to 5x5. Okay, so you can actually create a very simple formula to find this out, so you don't have to worry about like how the shape will change. And it's pretty straightforward formula. N is like your, and again, this is for one dimension. You can apply like the same formula for multiple dimensions, and you can achieve the values. Okay, so N is the length of your feature map. So in this case, in X direction, it's 7. And F is the size of the filter. In this case, it's 3. You just add that to 1. So that's input size, filter size, and usually like feature maps are like kind of even shape, right? So it will 7x7, 8x8 or something like that. And your filters are also like symmetric. You don't use like odd shaped filters. So then you can put like these values in this equation, and that's going to give you 5. You can replace with whatever values you have, depending upon your size of activation map and your filter. You can get like what's going to be the shape of the output activation map. Let's see like what are the different variations when we perform convolution. The previous case, we were trying to place this kernel at as many locations as we can. Now there is a concept called stride, and this is like one of the hyperparameters of your convolutional neural networks. Stride defines how many pixels you are going to skip when you move from one location to the other location. All right, so let's start from this location. If we have like stride of 1, then we will start from this location, we'll go to this one, so we won't skip anything. Okay, if we have a stride of 2, then we are going to skip one value. So this is the first location, then the second location is going to be this one, and then the third, again we skip one, we go to this. All right, so you can see that activation map of 7x7 filter 3x3, if we use a stride of 2, we were only able to place at 3 different locations, which means the size of the activation map is only going to be 3x3. Similarly, I think in the y-axis as well, you will only be able to place it like 3 different locations. So that's fine. So that's the concept. Now the question is like, why exactly we need stride? And there are a lot of reasons. I will give you a couple of them. One reason is if you think that your memory consumption of activation map is too high, and you don't want to actually process all the locations, you want to reduce that. Okay, so it in a way is like a memory optimization. Earlier, if you placed at every location, you are going from 7x7 to 5x5. In this case, you're going to 3x3. So it's kind of you're reducing the volume, or you can say like the shape of your activation map, you can try to optimize in terms of memory. So that's one motivation. The other motivation is, let's say you are using a very high resolution image. And in that case, if in a neighborhood, nothing is changing, when it's not like a drastic change as you move from this location to this location, then what will happen is the output activation will be very close when we place the kernel at this location and at this location. To try to reduce that redundancy, you can actually use a stride so that you don't place at every location and you try to skip. Okay, so that's like another motivation. And there are other reasons as well, but you don't have to worry about that right now. Okay, so again, the formula we had, we can update that to incorporate stride into to take stride into account. And the formula now becomes N is like your size of input activation map, F is the filter size, and S is the size of the stride. Okay, so this is your updated formula. And you can like put these values here, 7, 3, and 2, and that's going to give you your shape of your output activation map. Okay, so that's that. Now another interesting thing is, since stride is a hyperparameter which you will have to set manually, like when you design your convolutional neural network, so you'll have to be a little careful about that, because it may happen that like some strides are not compatible with your filter, or you can say like your activation maps. And so let's try to understand when that may happen. So if you have an input of 7x7 and you have a filter of 3x3, and you wanted to apply like a filter with a stride of 3, you want to optimize like a lot. So then this will be the starting location. Then you will skip and then you will reach this location. Okay. Then you will see you can't put it here. And again, you are at the end, you're at the edge, right? Which means that when you are actually trying to transform this activation map into another activation map, when you're trying to extract features, you completely ignored this column and potentially the last row as well. So that's kind of like loss of information, right? And that's not, you don't want that. So which means that not all strides are actually compatible. And one simple thing you can do is you can try to find out for a given input activation map and the filter size, like whether your stride will fit or not. Okay. So a simple way is like you put that in your equation, and if it gives you like a perfect number, then that's possible. For example, if you use a stride of 1, it gives you 5. Stride of 2 gives you 3. Stride of 3 is giving you fractions, which means that these are not compatible. So a very simple trick to figure out whether your activation map size, your filter size, and stride are compatible or not. Okay. Now, this is another interesting concept, and we have seen this when we're talking about filtering. So padding is try to add like extra values in the borders so that you are able to place your filter at all the locations in your input image. Okay, usually like there are many different variations. I think we discussed those in the first or second lecture when you're talking about filtering. Usually zero padding is used. So by zero padding, we mean you just use a value of 0 in the border. Okay, so then if you're using a 3x3 filter, you can see that if you have these 0 values, you will still be able to place your filter at the first pixel location. Earlier, it was not possible. So that's one motivation to use padding. The other motivation is if you want to control like the shape of the volume as you move from layer to layer, then again padding is very useful. And in most of the cases, if you want to preserve the shape of your volume, then padding plays a very important role. Okay, so in this case, if your feature map was 7x7, you're going to use a 3x3 filter. You can just use padding of 1. And your updated formula will become something like this, right? And this equation is actually taking into account padding. So you can keep a note of this. I think later we will have a pop quiz based on this. In this case, n is your size of the input activation map, f is the size of filter, p corresponds to padding, like how many values you're going to add, s is the stride. So one thing you can observe here is these are just numbers, but in reality, like if you're working in two-dimensional space, your kernels will be 3x3, your input feature map will be 7x7, and in that case, again, your padding is, again, it's not going to be 1, it will be 1x1, and each axis represents padding in the corresponding dimensions. Again, your stride is 1x1, it's not 1. But when we are using this formula, we are just considering one of the dimensions, and we're assuming that like it's symmetrical. So we just have to do it once. But it may happen that if your input size is 7x9, then you will have to compute the values separately for 7 and separately for 9. And similarly, you can have odd shaped filters as well. Let's say 3x5. So we'll compute like these values independently for each dimension here as well. Okay, so usually we will see like a padding a stride of 1 where we are not skipping anything. Okay, so then the idea is if you want to figure out like what kind of padding you have to use so that you want to preserve the shape, then you can again make use of this formula. Because if you want to preserve the shape of the volume, then the output should be n, which is again the shape of the input. And then you can just solve this equation. You will have n, you will have f, right? You will have s. You just need to find the value of p. So this is just like basic mathematics, and p is equals to this f minus 1 over 2. So depending on the size of the filter, you can figure out how much padding is required for this kind of activation map if we want to preserve the volume. Now, the next interesting operation is pooling. And again, there are like several different reasons why pooling is useful in your CNNs. I will again give you a couple of those. The first interesting aspect is it helps you in reducing the memory consumption. And if you think that somewhere in the network, it's actually taking a lot of memory, or you can say like a lot of parameters, you can just apply pooling and reduce the size or the shape of your activation map. And pooling it's also called subsampling, which when we're discussing like CNNs at the beginning, we saw those subsampling layers in the CNN architecture, right? So pooling is exactly that operation. So that's one motivation. The other motivation is it helps you in bringing like some kind of invariance in your network with respect to translations. And this is very interesting because what will happen is, if let's say you have your image and there is some object in the image. So if there is some translation, like the position where the object lies in that input image, if that changes, so that will change like the activation values as well, right? Because the position has changed. But if you're using pooling, so pooling is basically looking at like a small neighborhood and then just aggregating the values. So if you use pooling, then even if you have like slight variation in the translation, the pooling operation will make sure that that operation or that translation doesn't affect the features which you are extracting. Okay, I will go over that in more detail. Let me first explain like how pooling works. So let's say you have this kind of activation map. This could be your image as well, or some kind of feature map, intermediate feature map in your network. And of course, I'm showing just like two-dimensional here. You will have like depth as well. So pooling means you consider like a very small neighborhood. In this case, the neighborhood is 2x2. Okay, so what you do is you, based on all these values, you just extract like one value. Okay, and there are various different versions of pooling. For example, like in this case, I'm showing you max pooling, and this is average pooling. Max pooling is you just pick the maximum value in this neighborhood. Okay, so in this case, it's 20. You can just pick that. And in this case, it's 30. You will just pick that. Okay, same for these two, in this case 112, in this case 37. Okay, so if you have such an activation map and if you perform max pooling operation on this, your output is going to be this. And similarly, average pooling is almost similar, but instead of like taking the maximum, it's kind of taking the average. So if you think about this, average pooling is in a way like using the box filter, right? A normalized box filter. But in this case, I mean, and of course, like implementation wise, it might be using box filter, but we don't care about that. Conceptually, it's different, right? We are just taking average of these values. So we don't need any kernel for that. It's a different story, like how it's implemented mathematically. But conceptually, we don't need any kernel. We don't need any kernel for max pooling. We don't need any kernel for average pooling. So this operation can be performed by just looking at these values. Okay, we don't need anything else. Now, again, there are some hyperparameters here. The first hyperparameter is what is the shape of like this neighborhood? And that you can say like is the way you're using, let's say, the shape of the kernel. You do have like a hypothetical kernel without any parameters. So in this case, it's 2 cross 2. So the pooling operation is 2 cross 2. And again, you have like some kind of stride because you're not placing at all the locations. In this case, the stride is 2. Okay, because this is the first location you put, then you skip this one and then go to this one. Okay, so those are the hyperparameters which you require for pooling operation. So as I said, like it makes your representation smaller. And ideally, I mean, you have depth in your activation map, but max pooling is performed independently for each activation map. You don't need like to understand the relation between those activation maps, and which is different from your convolution operation, because whatever kernel you have for your convolution, it actually spans across the depth of the activation map, right? It considers all the values. But pooling is looking at each activation map independently, which means that whatever depth you have in your activation map, that is going to be preserved. So if you look at this, if your feature map is 224, 224, and 64, okay, so 224, 224 is height and width, 64 is the depth. Then what you will do is you will take a slice of 224, 224 from this feature map, and you will perform the downsampling or the pooling operation. Let's say in this case, I think if you try to reduce it by half, it's going to be 112, 112. I think for this, you can use maybe a 2 cross 2 kernel with a stride of 2. That's going to give you 112, 112. And you perform this downsampling independently on all the possible slices of this activation map. And that will be your pooling operation. Okay, so then you can see that the output, the depth is not changing. It's still 64. But the resolution or the X and Y axis, it reduced to 112, 112. Okay. So two hyperparameters, kernel size and stride. Of course, like it's hypothetical because we don't have any kernel here. We don't need any kernel. So this is like, again, a simple example, 2 cross 2 filter and a stride of 2. And if this is max pooling, you will just pick these maximum values, 6 in this case, 8 in this case, 3 in this case, and 4 in this case. So let's try to understand like why it was translation invariant. For example, at this location, this pixel is actually highly active, which means that whatever pattern you are trying to look in your input data, it was present at this location. Okay, that's why you got 6. It was not present at this location. It's close to 0, right? Very small than 6. Now, let's say if you move that pattern or that object in your input image in this direction, or let's say towards top, so that it moved to this location. So then what will happen is in your activation map, you will get a 6 over here, right? Because it will be present at this location. But now if you look at the result of such a translation operation, this location is still going to give you a 6, because instead of at this location, you will have 6 at this location. So the final output is not going to change. So that's why this max pooling operation actually makes your network translation invariant. This lecture is again continuation of the previous lecture where we were talking about convolutional neural networks, and we went through like all the basics which are required, the basic fundamental operation which is used for convolutional neural network. We try to understand like what are the parameters which are being learned in this convolutional neural networks. And the last segment of this lecture is a case study on LXNet, which is like one of the first deep learning CNN model, which was used, which actually showed like very promising results on ImageNet data set. So we'll go through that architecture, and then I think the following lecture we have is part of that we'll try to cover today. So in that lecture we'll learn about how we learn these filters or how we learn these weights when we train these models on large scale data sets. Okay. So let's start with this case study. The name of this network is LXNet. And this is the architecture which you have already seen in the class. I think we discussed this when we were doing the introduction for CNNs. And let me quickly go through this. This is your input image, and the resolution is 2 to 4, 2 to 4. That's like the X and Y of the image. And in fact, this is a typo. It should be 2 to 7, 2 to 7. And I have directly took like this image from the original paper, and there itself it was a typo. So don't worry about that. Then 3 is like the number of channels you have in the RGB image. So the first layer is the convolution layer, and all these cuboids over here, which are shown, these are the activation maps, or you can say like the intermediate activation maps in the network. So the actual layers are not shown here. What is being shown in the architecture is just the volume, or you can say like the data points which are flowing in the network. The first cuboid is the image. Okay, so these are pixel values. Again, this is like the output of the first convolution layer. So these are all the activation feature maps. And again, this is like the output of the second convolution layer, and so on and so forth. Okay, so all these are activation maps shown, but how to get those activation maps will have intermediate layers. For example, we have a convolution layer here, we have a max pooling layer, again a max pooling layer, and there will be some convolution layer in between as well. And at the end, you have like a feature volume which is 13 cross 13, and we have like 256 different channels, which is also like the depth of the feature map. And eventually we try to compress it into a single dimensional feature vector. And after that, we have these dense layers, which is just the neural networks, like the fully connected layers. Okay, so 2 of these. And then the final one is the prediction layer, or you can also say like the output layer of the network, which predicts 1,000 different values. Right. So until this point, all of this is like a convolutional operation. And after this is like the neural network, the fully connected operation, which we discussed, I think, in the previous lecture. And okay, so that's like the overall architecture. Input, as I said, is 2 to 7, 2 to 7 by 3. That's the input image. In total, we have 5 convolutional layers. All right, 1, 2, 3, 4, and 5. And these volumes are output of those convolution layers. And convolution layers, you know, is nothing but like set of kernels. So to define a convolution layer, you should know what is the size of a kernel and how many such kernels you want. We have 3 dense layers. Okay, 1, 2, and 3. Third one is the final one. And finally, the output is 1,000 dimensional feature vector, because we have 1,000 different classes. So we want a 1,000-way classifier. And what will happen is each of those 1,000 values is actually corresponding to one class label. And if that value is high, it means that the network is predicting like that particular class. Okay? And all the other values should be low in that case. And these are just the terminologies which we used. So green is for convolution layers here. You can see like we have 5 different convolution layers. And this orange one is the max pooling layer. We have already studied what max pooling operation is. We also had like norm layers. So this was a different kind of normalization. It was performed to like limit the values of the activations. So we don't use this kind of normalization anymore. So these days we have maybe batch normalization, which we'll cover maybe, I think, in later part of the lecture. Or I think we have already covered this. So this is just norm layer, which is trying to limit the values of the activations. All right, then these FC1 is like, it represents fully connected layers. So you have 3 of those. Okay, so that's the nomenclature. Now let's try to understand what exactly this conv1 layer is. Okay, so input we know it's 227 by 3. The first convolution layer has 96 different kernels, right? And each of these kernels has a shape of 11 cross 11. So that's indicated here. And these filters will be applied at a stride of 4. So by now you should understand like each of these terms. 96 should be fine, that many filters. This is just the shape of the filter. And stride, you know, like when you move your filter, how many pixels you will skip in between. Now, with all these parameters known, you can usually you can easily use the formula which I showed you in the last lecture to compute what will be the shape of the output activation map. Okay, you can just apply like that formula. You have all these variables here. The other point here to note is it's just saying it's 11 cross 11 filter, but as you know that your filters are like 3-dimensional. So the third dimension here will be 3, so which is not stated here, but in fact the filters will be 11 cross 11 cross 3. Okay, the third part is implicit. Now, if you use like the formula which we already know, you can just put it there, and that will give you number 55, and that's why you have like 55 cross 55 resolution of the output activation map. And the third number, which is like the depth of the activation map, which is 96. This 96, as you know, is coming from the number of kernels we have. So we have 96 different kernels, which means we will get 96 of these activation maps. Okay, so that was the first convolution layer. And similarly, I mean, you can go through like the whole architecture here, and you will be able to understand like how we are going from 224 to 55 or 27 and then to 13 cross 13 to 256. You just need these variables and the equation. Okay, so now the question is, if you're using that many parameters, then how many total parameters or trainable parameters are present in this first convolution layer? And again, which is easy for you, you know that you have 96 different kernels. Each kernel has a shape of 11 cross 11, and you also have a cross 3. So which means that you have that many values to learn in this layer, which represents the number of parameters. You can just multiply those. So it becomes 11 cross 11 cross 3 cross 96, which turns out to be 35,000. Okay, so in your first layer, you have 35,000 parameters. Now let's move on to the next layer, which is max pooling layer here. Okay, so after conv1, you were getting 55 cross 96. After that, we have this max pooling layer where the filter size was 3 cross 3, and this was applied at a stride of 2. And again, if you apply the same formula here, that will give you the size of the output activation map, which is 27. All right, so that's how you get 27 cross 27. And the depth of the output will be 96. So in fact, the output of the max pooling is not shown here. Okay, so the output will be 27 cross 27 and then 96. And then after that, you will apply the second convolution layer, which is giving you this 27 cross 27 cross 256, which means in the second convolution layer, you might have 256 different kernels. Okay, so I think we had like a pop quiz last time, how many parameters we will have in this layer. So max pooling will have 0 parameters because we are not learning anything there, right? We know the function which can be used to perform that, excuse me, that operation. Okay, so after the max pooling, we have a normalization layer. And again, as I said, we just try to limit the values between certain range. So the size of the activation map should not change. It's just the values in that activation map will change. Okay, so the shape will remain the same. Now that was like the first 3 layers, but at the end, like this is like the full configuration of AlexNet. It's giving you the details of like for every layer, how many kernels you have, what was the size of the kernel, in this case 5 cross 5, and it's also giving you like the parameters, what's the stride, what's the padding. Okay, so all these numbers shown here, these numbers are not parameters of your network. These numbers are hyperparameter of your numbers. So there's a distinction between parameter and hyperparameter. Okay, parameter is something which is learned when you train your network. Okay, so those values in those activation maps, but the numbers which define the architecture, or which defines like the training of your architecture, those numbers are called hyperparameters. So parameters, you have no control, they will be learned during the training, but hyperparameters are something which will have to set even before starting the training. Okay, so all these are hyperparameters. Like how many kernels you have to use, you have to make a judgment. What should be the size of the kernel? Again, you have to make some judgment. Again, all this thing, like what should be the stride and everything. So the architectural details of the network, these are called hyperparameters. All right. So once you have these hyperparameters, then you know what your network is. I mean, with all these details, you don't need anything else. So irrespective of which deep learning framework you use, so deep learning framework is something like where you can train your models. Okay, so it's some kind of backbone framework which is provided. So irrespective of which framework you're going to use, your network will not change if you use like these set of parameters. Okay, you can use PyTorch, you can use maybe TensorFlow. The architecture is fixed. So now let's quickly look at like the number of parameters we have in each of these layers. The first layer we already saw that we had roughly 35,000 parameters. Similarly for Con2, you can do the computation here. You just multiply 256 by 5 and then by 5. And then you know that the depth of the filters in the second Con layer will be 96. Right? Because the output of the first layer gives you like a depth of 96. So the third dimension is implicit. So if you multiply all those numbers, it will give you around 614K. Similarly, you can keep computing these. So you have these numbers here. Okay. So now one interesting thing to note here is these are the number of parameters which you have in the convolution layer. But as soon as you move to the fully connected layers, so you can see like you have like 4096 neurons here and this one and 1000 in the last one. You can see the number of parameters, it's like a lot. I mean, it's too high if you compare that with the convolution layers. And again, the reason is in the convolution part, we are actually sharing the weights, right, or the kernels across space. But that's not happening when we have these fully connected layers. For each connection between neuron in your input layer to the neuron in the second layer, the next layer, you have a different weight. So that weight is not being shared, and that's causing like a huge jump in the number of parameters which are required to train in these fully connected layers. Right? So you can see like majority of the weights are actually coming from these fully connected layers. Now let's try to understand like what is the data flow in your network and what that data flow looks like. Okay, so again, this is like one sample CNN architecture where we have like different con layers. We have different activations. We have like cooling in between. And then finally, we have the fully connected layer, which is giving you predictions. So let's try to understand like how the data flows. Your input is, let's say, this image. And then what will happen is in the first convolution layer, you will have some set of filters, right? For example, in AlexNet, we had 96 different filters. In this case, I'm showing you roughly around 10 different filters. And each of this is like the activation map, or like you can say the output of one filter. So when you apply that filter to this image, you get activation map like this. Okay. And again, the second filter, you will get something like this. So all these are output from different filters. And since these filters are learned when you train the model, so each filter will be different. Okay. So, and you can see that like you know that when you perform filtering, you're just trying to match that filter with the input image, right? And if there is a match, you will get high activation. And you can see here that like at different with different filters, different positions are actually highly active. Okay, so for example, let's focus on the first one. You can see that like the bottom of the car, or you can say like some kind of shadow might be there, right? So that filter is actually is very sensitive to those shadows, and therefore, like at this region, you can see like it's highly active. Right. So by the way, the second column over here is after radio activation, which means that all the negative values are clipped and you only keep the positive values. Okay, so positive values means which are active. And here you can see that it's kind of getting highly active when you have like the hood of the car, right, which might be very shiny. So it could be the first filter responds to shadows, the second filter responds to like shiny surfaces, and so on and so forth. Okay, so you can have like a lot of those filters, and you will have these kind of activations. So each filter is responsible for detecting some kind of characteristic from your input image. And then again, these activation maps will go to the next layer. And again, you will get different set of activations. All right. And after each cone, you can select when you apply the ReLU, you are just clipping off the negative values. Pooling operation is nothing. It's just trying to reduce the resolution of your activation maps. So as you go down, you can see like what kind of features this network is trying to recognize. And at the end, what will happen is if a car is present, then that neuron will be very active, which is kind of a result of like detecting all these patterns, right? So all these patterns actually play a role in making the final decision. Okay, so these are like the activation maps inside the network. Now, so that was one part of your CNN. The other interesting part is like, okay, what will the kernels look like? Okay, so again, this is a very, very, I think, interesting question. But again, it's an ongoing research, and people are still trying to figure out like how to control these things and how to understand like the learning process in deep learning. So I will give you like a brief overview. It's like not a recent work, but what it tries to do is it tries to understand like what kind of features are being learned by different layers of your network. And the idea is, let's say this is your input image. The initial layers, the first few layers of your network, tries to learn low-level features because those filters are directly operating on your input image. And the filter size is usually very small, 3x3 or 5x5. In AlexNet, it was 11x11. But anyways, that filter actually operates on a very small spatial location. And that's why it's trying to capture like those small, like the low-level features. These could be like very simple shapes. These could be like edges, right? So you can see here that these low-level features will be, maybe it could be like edges in different directions or very, very primitive shapes. Okay, this is like a kind of a circle. And some of these are also trying to react to like different kind of colors. Right? Now, as you move deeper into your network, then if you try to think about this, then what's happening is you are kind of utilizing all these low-level features, right? Because all these features, if they are recognized, they will stack up like in the volume, right? They will go as a depth. And when you apply that kernel in like intermediate layer, that kernel is actually looking at all these activations at once. So then whatever decision it's trying to make, it's trying to make use of like make use of all the activations which are present at that level, which means that at mid level, you will try to like combine these and maybe try to learn some complicated shapes. Okay. And as you go deeper, again, it will be like a combination of those activations. So you will try to learn like more complex shapes. And here you can see that some of these are like very, very well-known patterns which we observe in our input images. Okay. And finally, we use like these activations to determine which object is present in your input image. Okay, so one last question I have for you is like these networks are called convolutional neural networks. Why don't we call them correlation neural networks? Because the operation which we are doing, it's actually correlation, it's not convolution. Right? The kernels, we are not actually trying to flip them and then perform that element-wise multiplication. We just take those kernels and we just do the correlation operation, which is element-wise multiplication, and then adding those values. Right? And which is fine, you can call them correlation, but it's just a term, so don't worry about that. Even if you call it correlation neural network, I think it will be fine. It won't change anything. the interesting thing is it actually doesn't matter, because the core operation between convolution and correlation, it's the same. As we discussed earlier, the only difference is you have to rotate your filters like twice, maybe in x direction, y direction, and then the operation remains the same. So rotating the filter, it's not a big deal. I mean, it's just like we'll have to write extra piece of code. So instead of correlation, you can also perform convolution operation. It's just it won't be efficient. Just like the rotation will add like some kind of computation overhead, and we don't want that. And at the end, these filters are learned. So the idea is, if the network can learn like filters based on the correlation operation, it can also learn the filters based on the convolution operation. Okay, so at the end, it doesn't matter like whether you call this correlation or convolution.